employ to find out more about a new compound. It is the method of choice for determining relative molecular mass. There are several types of mass spectrometer, but all work by ionizing the molecules in the sample and separating them according to their mass-to-charge ratios. This is a magnetic sector instrument. The center section of the instrument is a powerful electromagnet. The sample is introduced on the left of the instrument and ionized. The ions accelerate away into the first electrostatic analyzer, or electric sector. The ion stream passes between the poles of the magnet where the ions are deflected. The stream moves through the second electrostatic analyzer and into the detector. The instrument relies on the fact that heavier ions are deflected in the magnetic field less than the lighter ones. Ions of different mass require a different magnetic field to bring them to the detector. The instrument has a number of ways of producing ions using different sources. This is the outer part of an electron impact source. The heavy glass plate is used to contain the vacuum in the instrument. Without the vacuum, ions would collide with molecules in the air. The operator can isolate the source chamber from the rest of the instrument by using valves. This means that air only enters the source chamber, and the vacuum in the rest of the instrument is unaffected. This is the inner part of the ion source. It can be removed separately for cleaning. A beam of fast-moving electrons is used to bombard the sample molecules. The system works like this. Electrons stream from a heated cathode and fly towards the anode. The sample, which has been vaporized, is struck by the stream of electrons. An electron in the beam ejects an electron from the sample molecule. The molecule becomes a positively charged ion. The positive ions accelerate away towards the first electrostatic analyzer. One method of producing a spectrum is first to dissolve the sample in a volatile solvent. Methanol is often used. Typically, about half a milligram of sample is dissolved in 2 cubic centimeters of methanol. The instrument uses very small amounts of the sample. About 2/1000ths of a cubic centimeter of the solution is placed in a small crucible at the end of the sample probe. The sample is pushed into the source chamber using valves to retain the vacuum. The solvent evaporates, and the sample is vaporized by heating the probe if necessary. The operation of the mass spectrometer is computer-controlled, and the data produced by the instrument stored in the computer. On many occasions, the spectrum will contain a peak that corresponds to a complete ion of the original molecule, the parent ion. It may also show peaks from fragments of the molecule which were not only ionized, but also broken up by the electron stream. Any compound will produce a characteristic spectrum of ions and fragments. Unknown compounds can be matched by computer to known compounds using a database. This spectrum is that of methyl stearate. The parent ion is marked in red at the right of the spectrum.
X-ray crystallography is a powerful technique which enables us to work out the three-dimensional structure of a compound. This single crystal X-ray diffractometer consists of a goniometer on which the crystal sample is mounted in the center of the instrument. X-rays are produced on the right and detected by a scintillation counter on the left. The tiny crystal, which is the sample, can be rotated on the goniometer about 3 axes, under the control of a computer. The position of the crystal between the X-ray source and the detector can be adjusted. The black cup on the left is a beam stop. It absorbs the X-rays that pass directly to the detector without being diffracted by the crystal. The sample needs to be a crystal of high quality with well-defined faces. A good quality crystal is selected from the hundreds in the sample. The crystal is glued to a glass fiber, usually using epoxy resin. The goniometer head with the crystal sample is placed in the instrument. The position of the head is adjusted so that the crystal will be in the center of the X-ray beam. The movement of the crystal in the beam is under the control of the computer. The instrument can search randomly for diffracted X-rays using either a scintillation counter or Polaroid film as the detector. Polaroid film is being used here. For safety reasons, the X-ray beam can only be switched on once the lead glass door has been closed. The crystal is rotated about a vertical axis while it is bombarded with X-rays. X-rays that are not diffracted by the crystal are absorbed by the beam stop. Diffracted X-rays produce a pattern of dots, a diffraction pattern, on the film. This procedure can take between 5 and 90 minutes, depending on the quality of the crystal. This is the Polaroid film with the diffraction pattern, showing where X-rays have struck. The coordinates of these dots are measured and that information fed into the computer. The pattern is symmetrical. The symmetry depends on the crystal structure. The instrument uses these rough measurements to search for the accurate positions of the spots, using the scintillation counter to detect the X-rays. The instrument can take from 8 hours to several days to record the position and intensity of the X-ray diffraction pattern. A computer analysis produces an electron density map like this example. Because heavy atoms have more electrons than lighter ones, the density map can give clues about the location of atoms in the structure. A graphics program allows the structure to be viewed from any angle, as in this example.